So, welcome everyone. Today is the first session of our primer series with Eval.Science. And the idea of this is how do we also, as we are doing this pilot, how do we build a strong foundation, with the right principles and tools that already exist so that, our understanding of the mechanism gets deeper. So I think that's the idea behind this, doing it for the first time. So yeah, super open to the feedback and see how this goes. Our first guest is David Dow. David, I don't think I can do justice in introducing you, so why don't you go ahead and introduce yourself?
I'm David Dow. I'm a core team at Eval.Science, together with Sejal, Nidhi, Devansh, and Lau and others who hopefully will join later on. We started Eval.Science because we think there's a lot of cool science that we want to trickle down into the PGF space, uh, and we want to really um, see if we can have a more scientific principle to like funding, allocation, and also just want to jam a little bit on the research and teach a little bit on the stuff that we read about. So this will be a primer on cooperative game theory and Shapley values. It's a little bit related to my PhD, but like on the introductory level. And I feel it's something that would be wonderful for the community to hear about, to learn about, and to apply potentially. And Eval really aims to have a more series of primer series that we are also super open for suggestions on topics that you would like to hear about. Otherwise, we are in our internal core team will discuss topics we feel would benefit the community. But yeah, super stoked of teaching. Um, so I'll get started with a super chill like intro. Welcome everyone. So a couple of things to ensure that we have a good time together. Please keep your microphone muted when you're not speaking, but always feel free to turn on your camera and say hi. And at any time, if you have questions, please feel free to write it in the chat. I can see Marco already turned off the camera, which is exactly the opposite of what has been said. So let's get started. Where are you joining us from today? Feel free to share your answers in the chat. India, Cape Cod, Switzerland. Hi, Marie-Claire. New York, super cool. Earth. Oh, cool, Las Vegas. So, next question, a quick vibe check. Feel free to also write your answer in the chat box. Briefly write a number of how you feel today, corresponding to one of these animals. And also, if you like, maybe you want to unmute and explain how you feel. Oh, 8, 2, 8, 5, nice, 7. Very cool. Awesome. Awesome. I'm definitely also more on the 8 and 9 side right now because I'm really excited to show and teach this lecture now. So, welcome everyone to first primer series on Eval.Science. Today we're going to talk about cooperative game theory and Shapley values. So, let's get started with an overview. We want to talk a little bit about cooperative game theory. I'm sure some of you have heard about game theory, but we're going to do a really super gentle introduction on game theory itself. Then we're going to talk about Shapley values as a really fair allocation solution. Maybe some of you have heard about Shapley values, many of you have not. And I think it's a super cool, super simple idea that whenever you're going to talk about and see things in the future, you're gonna be like, oh, Shapley value, that's a way to do it. We're gonna talk about Shapley values and applications, and then I wanna open it up in with Q&As, and the whole session will be roughly 45 minutes, maybe a little bit less, depending on Q&As. So we have plenty of time afterwards to discuss stuff. And again, if you have any time questions, feel free to write it in chat or like unmute your microphone and ask. So, cooperative game theory, what is that? So when you look at game theory is pretty old actually. And maybe some of you have heard about von Neumann. He is the guy who helped us create the computer architecture chip. So we have this von Neumann chip, like a CPU, memory, and stuff like this. But he is also credited to be the inventor of game theory. In 1928, he published a paper called On the Theory of Games of Strategy, which introduces games as a really cool mathematical tool to think about strategic behaviors of like people and coalitions. And in essence, a game has three things. It has a set of players, so people who play the game. Each game has a set of actions, things you can do, and rules, things you can do at a certain time and not allowed to do. And then, very importantly, a game has a payoff function. So something that will basically pay you once you have done something. Those three things are defining a game mathematically. And in theory, we assume that people who play, they want to maximize their score, the payoff, right? Like you want to maximize your high score in a video game, you maximize potentially money in like economic games, you maximize status in the academic game. So you have something you want to be maximizing of, and you're also expecting that other people you're playing the game with, they also want to maximize of. So let's start with a game that some of you have heard about. It's called the Prisoner's Dilemma. And in this game, this is called a non-cooperative game. I will go into the difference between cooperative games and non-cooperative games in a second. But in this game, it's a two-player game, player A and player B, and they have a set of two actions. Player A can stay silent or testify, and player B can stay silent and testify. The scenario is this: two kind of prisoners have been caught, but the judge is trying to get out what they've done or not, and they are put in separate rooms, and now they can choose if they want to like testify and like tell the judge what the other did in order to get a little bit of better years and less jail, or stay silent and hopefully hope that the other player also stays silent, and then both of the players like get less years in jail, right? So you can look at it as a payoff matrix where if both stay silent, both only get 1 year in jail. If A stays silent, but then your friend B testifies, B will get out for free, so he's smiley, but you will get 3 years in jail. If you testify and B stays silent, you will get out of jail and you will put your friend in 3 years of jail. And if you testify and your friend testifies, you will both get 2 years. So a really suboptimal outcome. If we look at it from a mathematical perspective, and again, thinking of the assumptions we had, that you want to maximize your payoff, which means you want to have the lowest negative value, then if your friend, so if you're player B now, and you assume your friend is staying silent, then you look at the options, and then you think, I mean, obviously, if my friend stays silent, I need to testify because that's gets me like less punishment. Now, if your friend testifies, and then you're looking at your options, you're like, okay, then I also have to testify because otherwise, if I stay silent, I will get -3 years, right? So basically, what this means is that you will always testify in all responses from whatever your friend is doing, independent. Testifying is the more stronger option, and it creates this kind of we call it the Nash equilibrium, or this kind of solution that if this game is played once by both players, they will tend to defect instead of cooperate. It's a very sad and very like dark outcome of this mathematical model, but it's oftentimes the case for these one-player prisoners dilemmas. But there's a second version of it, and when this kind of game has been introduced first time in a university, obviously, and was played randomly, people noticed that, well, many people actually cooperate. They don't like defect. So are they not rational? And the fact is, what happened is the students played many, many times this game. And what happens is when you're playing this game many, many times, then when you testify and you happen to play against the same player who remembers that you like testified and defected, then this other player that you play against, he might be disappointed at you And there is even like you will be forever stuck in you each other betray each other, right? And in that way, because you have to play this game many times, potentially your reward is actually lower than when you have just decided to cooperate. So in this version of an iterated prisoner's dilemma, it's a really cool insight from game theory. Actually, cooperation emerges as a dominant strategy and not just like um, defection. So this is the small bridge. So you've seen now game theory. Probably you have heard about this prisoner's dilemma. And I wanted to show you the prisoner's dilemma to see what this game is consisting of. But now I want you to keep that in mind. And I want to introduce cooperative game theory, which is a branch of game theory that is a little bit different from what you just saw. In a cooperative game, you have agreements that you can do. You can do coalitions. Um, so, for example, if you have player A and player B, in a cooperative game, actually, you can join together and work together through a binding contract. In the other game, the non-cooperative, the prisoners could not talk, they could not like work together, right? So it's impossible. But in this new version of game theory, cooperative game theory, you can actually formalize coalition. That's number one of the difference. Number two difference is that you can freely communicate. So you can negotiate with player A and player B and say, okay, maybe do you want a little bit this, you want a little bit this, to reach an agreement. So it's allowed to basically for you to reach an agreement. Then TU games, you might see this one day. So I just put that abbreviation for you. We use this in the scientific lingua. It's called transferable utility. What it means that in the prisoner's dilemma, when you get minus one, like when you get 1 year in jail, you cannot take that 1 year in jail and you give like 6 months to your friend and 6 months to yourself. So it's not transferable. You cannot split it. But in the cooperative game theory, whenever you get a reward, like $100, your coalition can decide who of the players get how much money. So when you get $100, maybe you can decide if it was a two-player coalition, player A and player B both get
Yeah.
50.
Right. Okay, so
Yes. Oh, sorry. Yeah. And then
There
the
was also
last part,
yeah, there was also a question which you can take after you. Yeah.
yes, yes. Let me see. I'm minimize the chat a little bit. So if there's a question in the coalition not enforced, could you explain that briefly? Yes. So the coalition not enforced in the other slide here, coalition not enforced. This is basically in the non-cooperative game is when the coalitions are basically not happening, right? Like cooperative game theory again deals with coalition. You will see that in a second when I introduce you the next game. So in the characteristic function, remember we had a payoff matrix for the prisoner's dilemma. You do this, you get 6 years, 2 years, and 2 years. You do this and do this, you get minus 1 year and minus 1 year, right? This is a payoff matrix. In a cooperative game theory, we introduce instead not a matrix, but a function that takes in a coalition and gives out a reward. So you take player A and player B, and then this function says those two players earn $50 together. You take player B and player C, those two players earn $40 together. It will be more clear in a second. Okay, the first game I want to introduce you to in cooperative game is quite a cute game. It's called the glove game. It's a real game that that economists have been using to introduce cooperative game theory. And in the glove game, you have three players. You have player A who has two right gloves. You have player B who has a pair of like left and right glove. And then you have player C who has only left gloves, right? So now each player can actually sell a pair of gloves for $100, but only a pair because like not having a pair is kind of useless, right? So one full pair of gloves earns you $100. So what happens now? If you look at it and player A, B, and C decide not to form a coalition, not to work together, then Player A will not earn any money because like no one's gonna buy two right gloves. Player B has a pair of gloves, so will earn $100 if he or she sells it. And player C will also earn nothing. So now we're allowing coalitions. So if player A and player B join, they will have one full glove and then two left gloves. So they can only sell one glove, so it's just $100 they can earn together. If player B and player C work together, it's the same thing. It's only one full pair of gloves. But if player A and player C work together, suddenly the two left and the two right mix together, and you have two full set of gloves earning $200. So initially, if A and C work alone, they would earn nothing. If A and C work together, they earn $200. And if everyone works together they earn $300 because now you have three set of full gloves. The big question in cooperative game theory, I feel, which is equally important for whatever we do in Web3 and on-chain and public goods funding, is how do we divide the value such that this coalition is stable and fair? We're looking for a fair and stable allocation of the profit that was made. Let's think about this. Let's say randomly we have allocation number one. Let's say we give player A $105, player B $90, and player C another $105. What do you think will happen? Suggestions in the chat? Yeah, I mean, B will be not happy, right? Exactly. B will sell directly because remember, B can earn $100 just by herself. So why should B accept this? So what will happen is the coalition will break. It's unstable, and B will leave and earn more money by being a single player coalition, leaving player A and player C with nothing. So, second trial. Let's see if we can get this time a little bit better. Um, if A gets 190 and B gets 100, and let's say C, he's a nice guy, but he only gets $10. So what will happen now? Any suggestions? That's stable now, right? That should work. That is correct. So C goes rogue. What will happen is C will leave and will try to bribe B because both C and B, let me just, oh, because both C and B earn $200 together. And then, oh, that's actually not correct because they only earn $100. But basically, C could just say, okay, yeah, I mean, C would be probably rogue. Yeah, this is also not working. So this is we need a stable and fair allocation. This is wrong because like they don't earn $200 to each other, but C would just be rogue and say no. So we really need a much better allocation schema. We want that is systematic, like something that we can compute for all possible coalitions, right? Something that always come with a solution where we won't have like an argument. And the Shapley value now arrives as a fair allocation and solutions schema. And so what will happen is, does anyone have an idea what the Shapley value here could be? Like what would be a stable allocation for the three players?
Uh,
Yes? Yes. Potentially equal to all, yeah. So let's see. So the Shapley value is a way to split the funds into a provable stable allocation. and was invented by Lloyd Shapley, 1953, a mathematician who ended up winning the Nobel Prize in Economics, not necessarily for the Shapley value, but for another contribution he did for the matching markets that are used. But he is considered to be one of the big game theorists of our time, and have provided a lot of this. Um, so in the Shapley value, um, and why it's so beautiful is that it's the only allocation schema. It's provably the only way to allocate the money that has this allocation has three properties. It's efficient, it's fair, and it's linear. Let's go through them. What means efficiency? Efficiency means that this allocation scheme, the Shapley value, uh, all the value is spent and nothing is overspent unnecessarily and no money is lost. That means that whatever the free values of these three players will be, it will sum up to the total amount of money that is basically getting in. So all those three will be $300. Fairness, the Shapley value will guarantee, by the way it's computed, that if there's a second player, if player B is basically doing the same as player A, um, you would have the same amount of money allocated. So if there's another player who's exactly one-on-one, everything the same as what you're doing, then this player and you will get the same reward. And if there's a player that actually contribute no value at all, this player will get $0. So that is guaranteed in the Shapley value calculation. And another one, linearity, it's the hardest to understand in the Shapley value. But what linearity means is if you have multiple products, if you have a normal gloves and then you have like a premium gloves that you can also additionally sell, then the Shapley values of the normal glove game and the Shapley value of the premium glove game, when you add them together, is the same as the Shapley value of when you would sell those two gloves together. So linearity means just you can like decompose games and add games together. So a little bit of math to show you that it's not trivial. So the Shapley value by definition is this. It's the expected marginal utility of a player. But let's walk you through what this means. So the average marginal utility of all possible coalitions is the following. How you would calculate is you would look at all possible coalitions ordered. Um, for a three-player game, it's six possible coalitions. It's A, B, and C. It's A, C, and B. It's somewhere where A is the second one and somewhere where A is the third one. So these are all possible coalitions. And you can see that the order is very important. The order of is A first and B and C, or is A second and B and C. And so there are six possible coalitions. And now what you're gonna do is let's look at the marginal utility increase of them. Let's look at the two center ones. The two center ones basically mean, if you look at it, that player A would just join, for example, Divansh, or would just join player B here. And so you can see, okay, player B has her own kind of like marginal utility. She earns $100 for gloves. Now I join. How much do I increase? By nothing. I do not add any value, right? So I add $0. So now I look at player C and I'll join. And then suddenly, oh, from $0, we have $200. So by adding and by joining player C, I have $200. So this is my marginal utility increase for $200. Now let's look at the other two coalitions here. This is the grand coalition. So when I join already a group of two people, I actually increase player B and player C. They previously only earned $100. Now with my extra gloves, they earn $200 extra. So I earn $200. And remember this big coalition, because we care about the order, we have to count twice. Because sometimes player C is first and player B. And so this grand coalition is counted twice. And in this one, we also earn $200. And last, this one is the most difficult to understand. Basically, when you are the first in order, that means that nothing came before you and then you just joined. So nothing, no one sells anything is $0. And then when you come in, the difference of nothing, $0 and you, that's your marginal utility increase as a single person coalition. And again, 2 times because of the order. So a question in the chat. If the player B is the unique seller of a good pair of gloves, wouldn't the price increase? So this, I think the demand and supply is here not considered. This is purely strategic. Like we assume that the price is fixed and we will figure out, depending on the resources every player has and the value every player contribute to like a team, how much like what is the fair payment for a team member? That's basically what it focuses on. So it's separating a little bit from the pricing, but a really good question. So now we have all the values calculated. So $0, $200, $200, $200, $0, $0. These are all my marginal utility increases. And now what we can do is we can calculate the average. So we divide by 6, which is the average. And we have $100 as the Shapley value. If you do this for all the other players, you will receive exactly what Devansh has hinted, that the Shapley value of this specific game is actually an equal contribution to all of the players. So this will create a stable and fair coalition, meaning there's no sub-coalition where it's incentivized to break out and leave this bigger coalition because the sub-coalition could pay you a little bit better. So this is a fair allocation. Shapley values don't have to be always the same. So there's another game, for example, supply chain game, where player A has some raw material, player B owns the factory, and player C basically gives out the distribution. And now maybe the whole supply chain earns $500. So they provide different kind of value sets, and it will be a little bit different as well. But let me see what questions we have here. So there's no incentive for player B to join the coalition since it will be $100 person regardless. That is true. So B doesn't really gain anything from the coalition, but B wouldn't also lose anything from joining the big coalition. So in a way, B is like rationally indifferent from it, and that's why the grand coalition can exist, because potentially it also doesn't matter for her to why not join. So it's stable in the sense that she can be like a jerk and not join, but then she also doesn't really like she doesn't have an incentive to not join either. So that's the reasoning here. The order is important because sometimes the way you calculate the characteristic function is depending on the order. And that's something you can see potentially in this game, where when the factory comes in and then the wool comes later, potentially that is less useful than when the wool comes in first and the factory comes in later. So the order basically allows you to be more general when it comes to value allocation. So in this supply chain game, I just make some rules up. Like the wool itself would not sell any gloves, so $0. Maybe player B already has some wool in his or her factory, so he or she can create some like small gloves, $100. And if you only have the truck, you can only kind of distribute and sell what is existing already. So player C would earn only $50. In a game like this, the Shapley way wouldn't be the same. So this is just adding and doing the same calculation as previously, where you have the Shapley calculated for the players, and $167 would be player A, $200 player B, and $133 player C, who owns the factory. So the Shapley gives you kind of also a sense of who's the most important team member in the coalition, and therefore it's really interesting also to use to interpret the value of certain kind of dependencies and projects. And now, finally, let's talk a little bit about application of the Shapley value. So, of course, deep funding is an application for the Shapley value. The Shapley value provides you with a stable and fair allocation that scientifically, people have been doing some studies, are quite similar to how a human would judge. So when I asked you initially, how would you split the value such that it's fair in a grand coalition? Like someone said 100 or 100, 100 equal, right? And so the Shapley value will oftentimes come to solutions that mathematically has these really beautiful axioms, guarantees, but at the same time also often reflect human judgment. So in the deep funding case, where we have to calculate the value of dependencies, one can try out different kind of dependency coalitions and see how you would need a characteristic function. You would need to have a function that says, okay, only those four. If we leave out this one, how much would the value change of the package? That is probably like an agent allocation problem where we need to figure out the characteristic payoff function. But if you have this, you can calculate the marginal utilities and you would come out and get the Shapley value. Another useful thing for Shapley is governance, because Shapley is used, for example, to calculate voting power. You can see, okay, how would the election have turned out when this and this state are not part of it? And someone tried this for the presidential election, and you can see that certain states have a relative stronger voting power, a higher Shapley value, than other states who have a lower Shapley value. And that basically gives you and helps you interpret voting power of certain kind of things. So maybe really interesting for Web3 governance. Lastly, the field that I started to learn about Shapley very first in my PhD was on machine learning. So in machine learning, we currently have a field called data-centric AI, where we want to understand what data points are the most useful and what data points are the worst for a machine learning algorithm to be trained. What we do is we take the data set and we assume that the data set, each data point is a player in a coalition, and the whole data set is a coalition. And then we start removing and adding and retraining the machine learning model and measure the accuracy and the difference of the utility. That's how we can calculate the Shapley value for the data points. So last but not least, I just want to mention that the Shapley value, as you noticed, because we have to do all potential collisions, is super difficult to compute, right? Just by 100 players, we have 9.33 to the power of 157 coalitions potentially, so 100 factorial. Note the number of observable stars in the universe is just 10 to the power of 24. So that's very expensive and it's impossible to calculate. So what people do, just a little math for you to see as well, is that they do some sampling. And the sampling has really cool guarantees. What this means in normal language is that basically, if yes, calculating the exact Shapley value is super difficult, but just picking up one or the other and just calculating sometimes the marginal utility of this person, the marginal utility of this player, and averaging it slowly over time will, the more you do it, the more probabilistically you will reach the true Shapley value. And there's also some clever tricks how you can choose sampling, so how you can choose which player to add and which player to remove in certain kind of collisions slowly, such that you only need a certain kind of sample to reach a very confident estimate of the true Shapley value. With that, I'm gonna end my quick first primer of the Eval series. I'm gonna try to answer some of the questions and also open up for Q&A. So one of the questions now is Tanisha, the Shapley value assumes that utility is transferable among players. What if utility is not transferable? If utility is not transferable, meaning that these $100 are stuck and like the coalition will just get it, then the coalition itself has no way to reward its players. And we will probably fall into a non-cooperative game where coalitions are basically kind of competing with other coalitions and there will be strategic behavior. So transferability of utility is really, really important, but oftentimes given in at least the cases that we talk about because money is fungible and we can separate it out, but really good question. Devansh is asking, okay, still a little confused how this is different from just calculating a person's marginal utility and paying them that. So a person's marginal utility, when you only consider one collision, um, is basically only capturing one possible scenario. So it's basically the same thing, except for calculating all possible marginal utilities and paying them. So the Shapley is basically the way you calculate this is actually calculating the marginal utility, but for all possible worlds where this player could have been in any possible coalition, and then you average it to get like an expectation. Anshuman is asking, okay, question about the second axiom. Allocated values must be equal to contributions made. Is there some debate around how contributions are valued? I ask in case there are games in which the sum is greater than its parts. Really good question. So where the sum is greater than the parts, usually what happens in the first axiom, I think the rationality, is that the largest possible payout is the sum of the Shapley values will the sum of the Shapley values of each individual player is total to the total, like the largest payout of the game itself. Because that's what people want to strive towards, to distribute this money towards the players to keep the largest payout. And in that way, it kind of considers the fact that the coalition just earns more than the single players itself. I'm not sure if that answers the question a little bit better or not.
Hi, David. Oh, sorry.
Yeah.
I just have a quick question.
Yes.
So currently I'm studying Shapley robustness, and I was wondering if you have any thoughts about, like, I would assume, especially in data, because data additivity is not guaranteed, and there's been a
Yeah.
couple papers about this before. If you're sampling to estimate the Shapley, I would assume that there are certain data points that are more sensitive, like in this kind of order matters thing. Like there some data points are really sensitive to coalition structure and some data points are less sensitive. And I was wondering if there's some framework for measuring like for the robustness of an estimated Shapley.
That's a really good question. So we looked into this briefly with group testing. So in group testing, you have to figure out like a good kind of dependency model of to make sure that you kind of smartly sample these players, these data points, to get as much information out from that small test that you can. But it really assumes it it doesn't really assume, I don't think it really assumes robustness in that sense. So in that sense, I think it's limited because it's kind of like a statistical optimization. So I think if you want to look for variance, like what happens if you really potentially happen to remove the unlucky Shapley that causes the whole mess, um, I think there is I'm not aware of any kind of like potential ways to measure this, but I do feel like when we kind of get accidentally some Monte Carlo samples of the really negative Shapley wave, then in some of the collisions we'll see a huge variance, and that can give us some insights that this specific Shapley wave is probably not as robust as we expected, and that could potentially guide us towards developing a more principled framework and picking it out. But I'm not aware of like one that really finds out the robustness and considers that in the sampling as well.
Okay, awesome. Thanks.
I know of some work that probably you're aware of as well, where they look into distributions of the data set, and that kind of marginalizes out of that. And that's maybe also one way to go into. But really good question. So can you do this presentation on Twitter eventually? So this is a cool question. Yeah, I might. The Primer series is really meant for introducing this really beautiful concept. I feel like people should know more about this, especially the on-chain Web3 community. So yes, we will share this presentation in our Gitbook, and we will also add additional material on this. Nidhi, Sejal, Devansh, Lau, and others are working really hard to making this content accessible for all of you. So the answer is yes. This is so interesting, Tanisha. Have you explored modular Shapley value? Super cool. For example, weighted Shapley value, where certain players' marginal utility value has a higher weight, multiplier based on a player's contribution or past expertise. Yeah, weighted Shapley values is really cool. So there are related works. I know in the area where I kind of like did my PhD on, which is data variation, where we looked into weighted Shapley values specifically for asymmetric cases where a certain kind of thing should be more important because it causes another thing. Um, that's where the directionality actually matters. So there is work on this. There's also work on time-dependent Shapley values as well. But this is like a whole. It's actually so. This is really the primer. This is the beginning explanation of 1953. This is Shapley value, but then there is so much work on the Shapley value itself because it's such an intuitive way to calculate things, but mathematically such a difficult thing to evaluate and offers so many challenges that people have been looking into that. Maybe I will do a Shapley deep dive to answer some of the questions that also Michelle asked that are quite interesting to look into as well. Um, Anyone else want to present in the next primer series? That's a really good question. So that's something maybe we could do. Maybe, yeah, maybe Michelle could do some of her research. I would think that would be really cool. Or Tanisha. Yes. Cool. Any other questions? I'm so excited to teach. I like it. This has been fun. Also, thanks so much for all your questions.
Amazing. The session is recorded. I know if some of us want to watch again and if people who've not joined will share it. Also, maybe this is like more an open discussion, but we were thinking of what should be mm, like when should be the next session. So any suggestions? Like, do we want to do one before holidays or should we now do in January? So yeah, also open to suggestions there.
I think for deep funding, so now we maybe like having a small community sesh on deep funding itself. Um, I feel deep funding is super cool, and it's potentially a selling point in impact evaluation for our community. Like funding open source dependencies is just the first step towards funding scientific networks. That's something that Sejal and I have been like discussing. And I feel one of the sessions that we could maybe think about would be metrics of impact itself, right? Like Shapley values and is kind of a fair allocation scheme. Cooperative game theory is a way to think about. One of the algorithms I'm sure that many people will leverage at the deep funding competition are potentially graph neural networks, graph network analysis. And I think this could be maybe an interesting topic to discuss next.
David, can I just jump in if others don't really have a question? This is kind of a very noob level thing, but I was wondering as you were going through your presentation, there were two terms that you used. One was a characteristic function, and
Yeah.
the other was a payoff matrix. I'm not a mathematician. Um, I was just wondering how you would differentiate between those two, and what is the significance of that distinction?
They're really related. So it's just a way of how we basically it can be one translated to the other. A payoff characteristic function can result in a payoff matrix. Basically, it's all possible actions and then the payout. The characteristic function is basically kind of the rule of how collisions earn what, right? So the characteristic function of, for example, data variation is when your data sets are your players and you train a machine learning model, the machine model and the accuracy, that's your kind of characteristic function because the utility, like 90% accuracy, that's kind of the payout you want to give back to the players. A payout function, for example, the glove game is kind of how many gloves you can sell, right? And then the input of the players depend very much on the pairs of gloves that you have that you can sell in. So in many ways, the characteristic function is something that defines the game itself. So the characteristic function, very similar to basically identical to the payout matrix in the non-cooperative game, is defining the whole game. The payout matrix that you saw for the prisoner's dilemma is uniquely prisoner's dilemma. This payout matrix defines the whole dilemma, right? Because this people will choose the actions depending on this payout. And the characteristic function is the same thing for cooperative game. The characteristic function, how it pays you out, depending on what coalition, defines if you're gonna break up coalitions, if you feel unfairly treated when you get paid your transfer utility a little bit like this. So it really is the defining element of the game.
Thank you. Super useful.
Super cool. Yeah. So any maybe feedback for this session? Was it a little bit too easy? Was it a little bit too difficult? It was meant to be a primer. So it's meant to be for zero like prerequisites in introducing just this beautiful concept of the Shapley value.
Yeah, I see a suggestion by Devansh. Let's do the next session on 26th, which is next day to Christmas. So I think we can coordinate and see, who wants to take the next session, what it is going to be. So might be interesting to do like a Christmas special session. Yeah, I think
One of the things we can discuss as deep funding is to calculate some Shapley values for the dependencies that we have. So as you can see, one of the big problems is that our graph is humongous. And so we will not be able to calculate the exact Shapley values for all the edges. But we can take a small package, maybe with like 5 dependencies, and calculate the exact Shapley values of this and see how this kind of correlates to whatever the judging and the spot checkers are going to do. I feel this would be a wonderful bridge between what has been taught here, between cooperative game theory and deep funding itself. So you can see there's a lot of like connections between both things, like cooperative game theory and dependency graph funding.
also, David, do you have any resources that you want to recommend for people to?
Yes. So we're gonna release in the next couple of days a Gitbook version of this lecture because I did like all these kind of graphics and I'm gonna like put them on the Gitbook because like why not? They're cute. And then we're gonna use that also to link to potentially resources as well for you to read. I love just these old papers, the ones that I cited on in the like I just feel like there's so much to learn from. But there's a lot of really exciting novel work, recent work that Michelle also has hinted on that I think we can create a list on. I also have a GitHub README. Like I love to do READMEs of random stuff. One is on awesome data variation. I will link it later on in the Gitbook as well with some really recent novel research on weighted Shapley values, for example, and non-symmetric Shapley values as well.
Yeah, great. Definitely will get the details in Gitbook and share with everyone soon. So I think this was great. Devansh, I saw your comment. Yeah, I think that would be great if we can just take 10 minutes and talk about or share about deep funding, where we are, what's happening, and how everyone can contribute. That would be great.
Yeah, so I think the latest exciting update, which we haven't shared, is that uh, we're actually going to have like a version of the competition up this week itself using Gitcoin data on community contributions and Optimism Retro PGF data and Octant data. So basically, we're going to look at dependencies which took part in these rounds and simulate the comparison between both of them and see which one kind of did better. So we don't have an actual jury yet, which is collecting data. So instead, we're going to look at past data from Optimism and Gitcoin and other things and recreate these comparisons as though they were a jury. I think the larger goal is how do we simulate how much a project would have got if they took part in Gitcoin or Retro PGF without them even applying to it. So they don't actually need to shill their project to like every round, every 2 weeks. They don't need to shill it. They don't need to tell badge holders, please vote for me. We somehow managed to use data to say this is how much the project would have got if it had taken part. So so that's kind of what we have coming up. Once we get that full data crunched and uploaded as a competition on Kaggle, like then we should be able to share all the details of Shapley values and other things to kind of some of these to some of these competitions. I think the larger goal of like what we're trying to achieve here is kind of all of the grant systems we have right now require you to apply for them, and that actually leaves out a large number of people who don't apply for these grants. And so how do we give value to people who are creating it without them applying is point number one. And second, you often see the people who are closer to the customer getting money, and they don't have a way of passing it through to their people who help them make money, especially in open source software where you might have like Ethereum, which earns gas fees and transaction fees, but they don't actually manage to pass it to the software developers and open source contributors who make Ethereum possible. So how can we make it's like imagine a tree where you have leaves getting the sunlight, and the leaves were like keeping all that nourishment to themselves. They want like passing it down to the roots. Like it wouldn't work, right? So basically we want to try creating like something like Hidden Lives of Trees. I don't know if you read that book, but really recommend it. It's like basically we're trying to create that system where there are these like roots which are sharing resources with one another, and you don't and create a way to like measure value between them. So that's what deep funding basically is, creating hidden lives of trees with open source software contributions to start with. Because something we've heard a lot, I don't know if any of you saw the podcast with Vitalik, is people are trying to move away from public goods funding, which answers how valuable is this to humanity, which is actually a very hard question to answer, and instead moving to how much of this positive outcome is attributable to A versus B, which is kind of it's much more tractable in actually making progress. So that's kind of where the idea for dependency graph comes in. So I'm going to say a last point and then I'll stop talking to open it up. But basically, deep funding has three components to it. The first component is an unweighted graph. So you have like all the different dependencies, but we aren't assigning any weights to them. So we have that fully ready. You can go on github.com/deepfunding and you can find the unweighted graph. The second part is creating a market of allocators. It can be AI, it can be humans, it can be metrics based, which give weights to these graphs. So basically, it's like fill in the blanks where these are all the different dependencies, the unweighted graph. Now fill in the blanks with your answer. So that's the second part of it, which is what the contest is about. And the third part is how do we select which of the weights to go with? So that's where we have like some form of a jury which does pairwise comparisons. It's like almost like chess, like how in chess you have a ranking, right? And how is that ranking determined? It's by one versus one playoffs, and then you eventually get a rank on chess. So recreating that chess ranking systems or the ELO ranking systems to actually choose which of the models weights to go with on the unweighted graph is how I would explain it as simply as I can. And yeah, there's lots of prizes. Vitalik is funding the pilot. We have like $80,000 for interesting models submitted. So it's kind of a significant amount of funding if you're able to submit a model and it gets chosen as the winner. And we have $170,000, which will be allocated through your model. So whatever weights your model proposes, will actually get to allocate 170K as well. So it's a pretty cool one and short timelines. In 2 months, it's all going to be over. So it's good that it's like a quick sprint and not some long drawn out affair.
Yeah, thanks for sharing that, Devansh. And I think this week we'll launch the contest, hopefully, fingers crossed. So watch out for that. We'll share the details and would love for everyone to also amplify and refer people who they think should, submit a model. So that would be super valuable. And this is something that we, will probably continue doing. Like after our sessions in Primer series, we'll take 10-15 minutes to share an update about deep funding, and what is happening. So that would be great for everyone to also follow along. Um, what else? Any questions anybody has on deep funding?
Um, just to clarify the goal of the contest at least, it seems like you're looking for a counterfactual, right? Like basically, given that something isn't funded, what turning point would at what turning point of funding would have helped it like achieve a certain level of impact? Is that the logic behind it? Or I don't know if I misunderstood that.
Maybe David can add here, but I don't think that there's a counterfactual element over here. We are looking at this outcome was already achieved, which is a good outcome,
Okay.
and how do we determine whose contribution mattered the most,
Okay. That
mattered
makes
less?
sense.
Yeah, it's basically actually the cooperative game problem. Like, what is a fair and stable allocation that we're looking for? And we don't know how to compute this in a tractable manner because the open source dependency graph is humongous, that we're looking into. So we are right now thinking of having an AI model approximate the allocation values. And we are providing some human judgments, some weights from humans, and hope that we can kind of, so the human judgments might not be the Shapley values, right? Because it's computed from a human intuition. But that's something we kind of want to approximate for.
And I think one thing I'll add, which is why I'm so excited about it, is that it actually enables new forms of collaboration. That right now, there are like 6 different organizations that are partners in this pilot of deep funding. And if someone wanted to support the people making it happen, there's no easy way to do it. Like, how do we divide the money amongst the 6 partners and all is like pretty kind of difficult to figure out if you're not going to do an equal split. Whereas ideally at the end of this pilot in February, we create a dependency graph of everyone who helped make the pilot a success. And then someone can just give money and it gets divided according to those weights. So I think it's kind of neat, and especially in research collaborations, like kind of when you get prizes, a lot of people fight over like getting their share of the prize and all in research collaborations. So I think it can kind of be of great application in collaborations between organizations and also within collaborations.
One of the things that Sejal and I've been jamming about is that right now it's a dependency graph of open source software, but it could be connected to the citation graph of science. And that would be fantastic because we could fund science with the same kind of algorithm that we basically run and allocate the edge weights.
Yes. Amazing. So want to be mindful of time because for some of us it's 12:30 in the night, and it was such a great wholesome session. Like I loved it, and I think getting to be in David's class is always amazing because he's such a great teacher. So thank you so much, David, for taking out time making this beautiful presentation. Oh my God, I'm now such good ideas for, the presentations we make. It was so fun, like, it was so good. And so I just want to make sure everyone follow Eval.Science Twitter. Make sure you join the group. There's a lot of work happening, lots of new updates coming. Make sure you are in the deep funding Telegram group because there we will update everything and just share the next details of the next session. Follow the Twitter handles, follow people here. And yes, let's make impact together and bring this beautiful discipline to Web3. There's so much to learn from academics. So yeah, this is a way to bridge that gap also. And yes, once again, thank you so much, everyone. See you in the next session. Till then, see you in the Telegram. Bye.
You guys
Thank you, everyone.
next week.
Yes.
Thank you.